we're going to, for section 1.5, kind of wrap all this up and apply all of it at the same time, whatever. One of the things that you're going to notice is that they talk about vertical asymptotes. Remember that a vertical asymptote is an equation of an imaginary line that guides the graph. Okay? So just to give you an overriding example of what's happening in this section, if I take the limit as x approaches 0 of 1 over x, okay, as I approach it from the left, it's going to go down into negative infinity, correct? As I approach it from the right, it's going to go up to positive infinity. So we've already discussed that infinity is not limited. You can't limit infinity. So what we have is, first of all, negative infinity will never equal positive infinity. So this limit, just plain and flat out, does not exist, period. Okay. Now, what happens if I just do one-sided limits? So as x approaches 0 from the left of this function, that means the closer I get to an x value of 0, this is going to negative infinity. So what we're going to do is modify how you read this. So before, like in section 1.2, I think it was, we would say it didn't exist because you can't put a limit on infinity. What we're going to do now is we're going to say where it goes. So technically, what I'm saying is the limit as x approaches 0 from the left of 1 over x does not exist because the graph goes to negative infinity. So it looks like I'm saying it equals something, but just understand that what we're saying is it doesn't exist because it goes to negative infinity. So how are you going to know which answer it is? Because in 1.2, you had to put does not exist, and now all of a sudden you have to know. It will tell you to either use negative infinity, positive infinity, or it will say do not exist, okay? But from this section on, you need to understand that this is how we write it, okay? So let's try it again. What we have is the limit as x approaches 0 from the right of 1 over x. So as I approach 0 from the right, where is it going? So my tail is going up to positive infinity. So what I say is the limit does not exist because my tail goes to positive infinity. Okay, so this is how you'll write it. And so again, it looks like I'm saying it equals infinity, but you cannot limit infinity. So what I'm saying is it doesn't exist because that's where the tail goes. Okay. Now, last thing, if I ask you for the equation of the vertical asymptote, what you're going to do is take whatever your denominator is, after you reduce it, after you've done whatever, take that denominator and set it equal to 0, and if necessary, you're going to solve. Well, this one's already done, so I don't need to solve, but what you have is an imaginary line that guides your graph from the left and from the right. So you've got a vertical asymptote as this slices through the x-axis at 0, okay? Slices through the x-axis at 0, and it's dashed because it's an imaginary line. It's not part of the graph, but you need to know it's like an imaginary line that's saying this thing will never cross that line, and going this way, it will never cross the line. Okay, so the rest of it is just going to be being very, very careful how we interpret this stuff. So here we go. We have, consider the following function. I've got 1 over x minus 5, and I'm going to come at 5 from the left. So I know that 1 over x, my parent function, looks like the one I just had, but I shifted it to the left 5 units. To the right 5 units. So it looks like this. Okay. And there's your imaginary line at 5. How do I know it's at 5? Because if I sub in 5, 5 minus 5 is 0. My denominator is 0. My function's undefined. Okay, so what is my, and notice again that this has, you better put in infinities, either positive or negative infinity for an answer. Do not put does not exist. All right, so as I come at 5 from the left, where is my tail going? He's going down to negative infinity. So the way I read that in my head is the limit does not exist because the tail goes to negative infinity. All right, what about as I come at 5 from the right? He goes up to positive infinity. Okay? All right, let's try it again. So this one, I have a quantity squared, and I know that my parent function, it got shifted to the right 3 units. So he looks like this. Those are not corners, by the way. And then you have an asymptote at 3. Because if you sub in a 3, 3 minus 3 is 0. Divided by 0 is going to be undefined. So, I had to yawn, sorry. All right. If I come at 3 from the left, where is this thing going to go? It's going to go up to positive infinity. Another way to approach this, because you may have forgotten your parent functions, is your numerator is always positive. Okay? My numerator is always positive. What's going to happen to your denominator all day long? I don't care what you sub in for x other than 3. It will always be squared, which will make it positive. So because your denominator is getting infinitely tiny, okay, so like if I do 3.1 minus 3, if I do 3.01 minus 3, 3.001 minus 3, what ends up happening is the smaller your denominator, the larger this expression is. So the smaller the denominator, the larger the expression. So I know that they're both going to go to positive infinity because I drew the picture and I used some common sense. All right, let's do some more. I'm going to try so hard to make this in just 2 videos. All right, so determine whether I'm going to negative infinity or positive infinity as I approach negative 2. So as I come at it from the left, where does my tail go? He goes down. As I come at it from the right, where does my tail go? He goes up. Okay? Determine positive or negative infinity. And I'm coming at negative 6 from the left side. So there's negative 6. Okay? Where does my tail go as I come at it from the left? It's going to go up to positive infinity. Where does my tail go as I come at it from the right? It's going to go down to negative infinity. Okay, so you're just kind of sort of reading the graph and getting used to the idea that, hey, you know, I've got to explain why this thing is undefined. All right, so for this one, I'm going to square something. So where's my calculator? I found it. All right, so if I have, go to y equals, and then what I have is 1 over x squared minus 4. Oops, sorry, go back. Minus 4. Remember, if you don't have the new software, you better put that x squared minus 4 in parentheses. Make sure that your table is set to ask. Go to the table, and I'm going to shove in a negative 2.5. So I have stuff from the other day in there already. Negative 2.1, negative 2.01, negative 2.001. So I'm creeping closer to negative 2 from the left. Okay? And then I get a negative 1.99, 9, negative 1.99, negative 1.9. Okay? And then there's probably something else over there that didn't print. All right, so when I look at this, let's see if I can zoom in so you can see. Okay, as I come at this thing from the left, what's happening? These numbers are getting absolutely huge really, really, really fast. Okay? But from this side, they're going to be negative, but they're still getting bigger. So I'm going to approach it this way, and I'm going to approach it this way. So as I come at it from this direction, they're going to get bigger but positive. As I come at it from this way, they're going to get large negative numbers. Okay? So what does that mean? What is my graph approach? What is the limit as x approaches negative 2 from the left? And that's going to end up going to positive infinity. And then what's the limit as x approaches negative 2 from the right? Well, that's going to end up being negative infinity. And now you just got to pick the graph. So I'm looking for, as I come at it from the right, my tail needs to go up. So that's a possibility. Okay, that's a possibility. That's not, and that's not, because my tails go down. Okay, as I come at it from the right, my tail needs to go down. So from the left, it goes up. From the right, it goes down. From the left, it goes up. From the right, it goes up. It's not that one. It's got to be this one. Okay, or you can actually hit graph and make the picture of it. All right, so a few more. We've got find the vertical asymptotes, if any. What you want to do is, first of all, make sure it's reduced completely. Once it's reduced, then you're going to grab your denominator and set it equal to 0. So I have an x squared equals 0. Okay, grab your denominator, set it equal to 0, because that's where this thing is undefined. Take a square root, so I get x equals 0. So your vertical asymptote is x equals 0. If you just put 0, it's wrong. So as soon as you see the word asymptote, you had better remember, use an equation. Okay? So let's do it again. This is the sum of two squares, which means this is not going to be reducible. So, because this factors down to imaginary numbers. So, just to prove my point, grab your denominator, set it equal to 0, and solve. So I have t squared is negative 9. Take a square root. So I get t equals plus or minus 3i. So you have imaginary solutions. That means it's impossible in the real number system for this t equals 0. So what you have is d and e, because your denominator, good land of Goshen, your denominator cannot equal 0. Okay? So let's do another one. Remember, you're going to do this after you reduce. So I'm looking at this and it's pretty heifer scary. So I know that the top I can pull out a t, and that's going to leave me with a t minus 6. The bottom, I bet that's 36 squared. 36 squared is 1296. All right, so this is the difference of two squares. So this is going to be a t squared plus 36 and a t squared minus 36, which means I can factor one of those again. So this is going to be a t times a t minus 6 over t squared plus 36, and then a t plus 6, t minus 6. Okay, so my t minus 6 reduce. And then nothing else reduces. So what do I do in order to find the equation of the vertical asymptote? This, based on the last example, doesn't matter because it's imaginary solutions. This one does matter. So take that part, set it equal to 0, and solve. So you have a vertical asymptote at t equals negative 6. Watch out for your variables too, because they'll bite your face off. We're used to using x's. Make sure you use a t, because you're going to say, wait, I know it's right. No, it's a t, not an x. All right, so this one, actually, I'm going to come back to this one. All right, on the second video. I'm going to try and get through a few more of these. I need to know this has a vertical asymptote or a removable discontinuity. So again, if it's an asymptote, I cannot remove it. So come back up to this one. Okay, this one, the t minus 6 is reduced out, which means you would have a hole where t equals 6. But you have an asymptote where t is negative 6. Okay, so if it reduces, it's a hole. If it's non-reducible and you can set it equal to 0 and solve, then it's an asymptote. So this says determine whether the graph of the function has a vertical asymptote or if it has a removable discontinuity. And then graph the function using graph utility to confirm your answer. There's no graph to look at, so don't waste your time. So this, can I reduce anything? The top is the difference of two squares. And then the bottom is x plus 7. So I just removed it. So is it a vertical asymptote, which means it's set in stone? No, because I just removed my denominator. And so I have a removable discontinuity because I just removed it. Okay? Let's do a couple more. Hang on, that's a good place to stop. All right, so we'll stop there, and there's just a few more on the last video. Hang on, I can't find my mouse.